the lecture series from this morning. Apologies for absences in the previous class and things. There's been a few difficulties in arriving, but I'm here for the moment, and we're going to be talking for the next, for this week, talking particularly about collision detection and about the various methods of collision detection we can use in video games, which ones are most suitable in what circumstances, and how to do it best. So today we're going to be looking at some of the theory behind it, some of the most common techniques that we typically use in these sorts of things, and tomorrow we'll actually look at trying to use these in making a couple of basic games, and I'm thinking right now we'll make some kind of a platformer. So that'll be Friday's lecture, and we're just going to be looking at different kinds of techniques today and how they work. So let's sort of make a brief start on this sort of thing. Alright, so when we think about collision detection in video games, we tend to want to focus on those techniques that are most suitable for the situation. And the reason for this is because it's a fairly complicated procedure in most circumstances. Hold on, let me just... So if you think about like a basic game, you might have like, I don't know, a sort of like a spaceship. We'll do it for a second. Okay. So when you have like just like a basic video game, you might have something simple as just like a spaceship or something like that, and you'll give him a series of enemies that he has to fight through. It means that he might have bullets that are being fired, and those will in turn have to be sort of following some sort of form of collision detection to try to figure out, you know, how they react to when they hit various things and how they work. And then you might have a situation where you might have the enemies themselves. The enemies might look kind of like this, I guess. We'll make them... Let's do asteroids, actually. Asteroids are nice and easy. And so the question becomes, if you have a shape that kind of looks like this, which is kind of irregular, you know, it's filled in a few different areas, and then you've got a shape like this, which is also fairly irregular. Not so much that it's a real issue, but it's to some point. Then how do you decide what's the best way to decide whether or not these two objects have actually hit each other? And what we typically tend to refer to as this is it's thinking of the different techniques that can be used for collision detection. And the technique that we use is really important because the style of collision detection not only influences the way that the game plays, the rules which are abided by that, it also massively impacts the core mechanics of things, and it also impacts performance in particular. In games where there's a large number of assets around the place, the way in which you handle collisions really impacts the style in which the occurrence occurs. So we have to think very carefully when we decide about the various kinds of collision detection we want to use. So we're going to start with the most basic ones, and we're going to move on to more interesting ones sort of a little bit later down the track. So next start. So cool. All right, so we'll look at a few different techniques, and we'll see how we go. So the first one that we're going to be talking about right now is the absolute most basic, which is point intersects rectangle, which is the absolute most basic kind of collision detection that we can sort of have. Well, usually it is, or point intersects point if you want to go really sort of, if that's even simpler, but you very rarely use that. Probably the two most simple ones that we use, and that's where we have a single individual point that falls within the bounds of a particular rectangle. So if you think about this in terms of a pictorial sort of representation, then you might have it where you'll have a point, let's call it a bullet. It might look kind of like this. And the central pixel of that there has an X and a Y value. And then somewhere in the world, you'll have at least one rectangle. It's going to look like this. And the goal of this form construction is to determine whether or not this point lies inside this rectangle. And then that other example I had is where you might have a second point to see whether or not those 2 points coincide. So obviously the implementation of that's incredibly easy. The rectangle is a little bit more complicated. And it depends on how you've implemented your rectangles, how that works. So if you want to take this into like a example, suppose we take our shooting example we had previously, and suppose this is an asteroid. There we go. And we've defined our asteroid as being an object that in turn has sort of a surrounding rectangle that goes around it. And then we have this thing here, which is a bullet. And we want to find out whether or not that bullet actually sort of has hit that that asteroid. And we could use a technique where we sort of go more detailed, but the simplest one we can find is we just find out the edges of that, the most extreme edges of that particular asteroid by finding the minimum, the maximum on the x, y, and that essentially defines our rectangle, and then we just find out whether or not point lies in that rectangle. And the math for that is very easy. If we have essentially points, and we'll just call it P for the second, and P has an x and a y, and then we have a rectangle R, and rectangle R has, we're going to have this thing is going to have an X and a Y, or if you prefer it can have an X and a Y, and then usually has a width and a height. That's usually how rectangles are defined. You can also define them as being like a point, which would be like X1 and Y1, and then X2 and Y2 can also be another way of representing rectangles, which is probably more appropriate for our individuals. So you can just assume that X2 is just X plus width, and Y2 is just width plus height. So yeah, we can just sort of specify that there. So that's where we have then X2 is equal to X plus width, etc. So we can have it like that. And so we know that the point lies within the rectangle, and we don't have the special character for it. I guess that would be that one. Contains, or it's within. It lies within the rectangle, and we can decide that if Gabriel, could you please mute your mic? There's a lot of echo coming through. That's cool. All right. So P is we essentially decide that P is within R on the circumstances that P dot X is less. All right. Let's write this quickly. Is greater than R dot X. P dot Y is greater than R dot Y. And then P dot X is, so hold on, and then we can also go like this. Yeah, okay. Like that. So what that essentially means is that the point P lies between x1 and x2, and point Py lies between y1 and y2. And if you think about how that's going to look inside our picture, if we have any given rectangle, and you can think about the individual points, just so we'll just go like here. Very basic, it's not very good. So if you think about x, if you think about having the y points, this is y1, this is y2, those 2 points there, and then you might have the x on this side here, x1 and x2. A point is considered to lie within that rectangle if the p dot x lies between these 2 points, and p dot y lies between those 2 points. So that means it can lie anywhere within this area here, which conveniently enough happens to be inside the rectangle. So that's how we essentially decide whether or not a point lies within a rectangle. So it's a pretty basic, it's the simplest form of detection we can typically use. And we'll use this when we're looking at sort of very basic situations where most commonly we're working with a shape that is not very complicated or mostly rectangular. And also we have this sort of more space. Yes, go ahead, question. No, it wouldn't. No, this is a no. You would more commonly see this in like a maths textbook than you would actually as an if statement. So we're gonna have to edit test. The proper syntax for this would be if we were going to do some in Lua would be if p.x is less than r.x1 and p.x is greater than other way around is greater than r.x1 and p.x is less than r.x2, like that. That would be the correct syntax for that. So yeah, no, this is just a nice convenient way of writing in shorthand. Cool. All right. Yes, so thank you for clearing that up. Obviously, point intersects point or point is within point is incredibly easy. That's just a matter of seeing whether or not p.x is equal to p2.x, whatever you want to. So yeah, you just test those 2 points equal. We very rarely use that form of collision detection. Why? Because it is very rare for 2 points to coincide, especially if they both have velocity. And that's always an issue. So in the situation where you're trying to look at when the 2 points sort of touch each other, you have this problem where you'll find that very often you might see the points pass by each other. A common example is if you think about just like a basic shooting game. No, sorry. Suppose we have like kind of like a Space Invader style thing. So if you have like lots of enemies around the screen, and then you have bullets flying like this, you might have the situation where a bullet will lie directly beneath a something like this, and then essentially whether or not those 2 points will collide is now a random chance. It's going to depend on whether the bullet moves first or the enemy moves first, and so that can lead to inconsistent behavior, especially if you treat your bullets and your Space Invaders the same. So it's a less commonly used technique. We use it in Breakout. There's one example where we'll check if points intersect by testing all the points in our wall. And that's because the wall is stationary, but it's not safe for a lot of examples. So we don't tend to use that often. All right, so the next case is fairly easy, is rectangle intersects rectangle. All right, so, and again, like I say, the situation this is fairly clear. And you'll see this is commonly used quite a bit. It'll very often particularly be used for coarse grain collisions in most typical circumstances where we're looking at we're trying to make modifications and things to when we're trying to look at colliding sort of two large objects that are either of fairly regular shape, they're quite rectangular, or they take up a lot of space, or in a situation where they only need to be near each other and they don't need to be that sort of close. Brainstorm, could you please mute your mic? Okay, so typically what that will look like is if you've got a space like this. Thanks, man. And then you'll have a second one that collides like this. Okay, and there are a few different ways that you can perform this collision detection. I'll talk you through one or two of the theories, and then I'll show you the implementation I use for one of them. We're not going to use it too much today, but we'll just have a look at sort of roughly how it works and things. So one example that you can use for rectangles, and indeed for any other regular convex shape, that is a shape that does not have any sides that sort of come in on themselves, is what's called the separating axis test. And the separating axis test essentially is, if I have two rectangles like this, for example, and these two rectangles are not touching, I can find out if they're not touching if I can find essentially a line that has any angle in any direction it separates the two. That is to say, there's a line that can pass between the minimum and the maximum of both sides and not intersect with either rectangle. And it can be of any angle, any shape, so you could even have it as like sort of like a bent line if you wanted to. Yeah. Alright, so I know that my rectangles do not collide if I can find a line that satisfies that condition. That is to say, they don't collide with it too. And so, yeah, typically the way that we'll do that is we'll look at the edges, particularly the farthest edges of our shape. So this might be a square. So in this case, we'll probably use the square edges, and we would essentially find which edge we consider to be the sort of the closest one, something like that. And then we just look at trying to create that line. So for example, with this situation here, where we have two lines here, we would just create a line. So it's essentially based on that edge. Yeah. And then we would try to test whether or not that line intersects with this rectangle. If it does, then we know that this is probably a case, and otherwise it isn't. So you want to find what that edge separating thing is, which can be a little bit tricky. The approach that I've used in game utils, the one that I'm going to talk you through now, is more novel, and essentially that one is deciding whether or not the farthermost edges sort of lie within a series of points. I'll talk about the way the implementation for that works. So suppose we have two rectangles. We've got R1 and we've got R2. And we want to see whether R1 intersects R2. Alright. So the way that that I've done that for my testing, and the way that can be done in the clever way is, first off, you want to find the extreme edges and what side of the edges each rectangle has relative to the other one. So first off, you want to find if R1 is to the left of R2, or if it's to the right of R2. And the way you do that, obviously, is you just compare R1.x with So if R1.x is less than R2.x, then you know that R1 is to the left. R2. And you do the same test for above and below. Yeah, and so that way we can sort of tell general positions according to the previous two. So if we just go to paint here like that. So what if we have defined our two rectangles and we know they're colliding like this, so we'll just draw them out again. And then we'll have this one here. So in this instance, what we would do is we would compare the x value, so the side of this one with the side of this one here, and we would see, okay, is that x value less than or greater than that one? If that's the case, then this is it. So we know that the green rectangle is to the left of the grey rectangle, and then we want to see whether or not the y is greater than or less than the grey rectangle. Here it's less than as well. So we know that the green rectangle is above the grey rectangle. Yes, question? Yes, yeah, that's fine. I can paste bin that file for you, no problems. Okay. Yeah, so fair enough. Yeah. I'll give you guys a code in a bit so you can use that. So anyway, so we've got this these two, and we've managed to figure out what positions they therefore have. And so we now know, like, if they're to the left or to the right of that. So what we now want to do, essentially, is we want to find out whether or not, and this idea, I guess, I'm not sure if it has an official name, I just tend to refer to it as, like, the extreme edges rule. And essentially what we want to find out is we want to find out whether or not the extreme edges of these two shapes coincide, or if they collide. So if we know this one's to the left if we know our green rectangle is to the left of our grey rectangle, or at least they coincide, that doesn't really matter. What we then want to find out is we want to find out the difference between what we would call the rightmost edge of the leftmost rectangle, which is this one here, and we want to find out the leftmost edge of the rightmost rectangle, which is this edge here. And essentially, if those two edges intersect, then we know that the rectangles in some way or another overlap each other. That's what we're sort of roughly being able to figure out from that case here. And that's the case so where we also have the topmost edges. So if we just do that now, we know this is the topmost rectangle, so what we're going to find out is if the bottommost edge of the topmost rectangle and the topmost edge of the bottommost rectangle, which is this one here, if those two edges, that is, they coincide, that is to say that the bottommost edge of the topmost rectangle is greater, then we know that those two intersect as well. Now, it doesn't mean necessarily that if both those conditions have got to be held true for the collision to be detected, because if it is just one or the other, and I'll just show you the case here, you might have a situation like, let's go with this, for example. So now in this case, the rectangle satisfies the second condition, where the bottommost edge of the topmost rectangle and the topmost edge of the bottommost rectangle do coincide. You can see that the edges there are separate. So in this case, the topmost edge of the bottommost rectangle is less than this edge here. So that way we can't assume a collision, we just know that this rectangle is it intersects on the y-axis, if you like. And then we want to see whether or not it intersects on the x-axis. And if it does both of those things, as I say, it intersects on both the x and the y-axis, then we know that our two rectangles coincide and we have a collision. So that's the way that we would do that. So let's actually put that into our test file so we have that out nice and clearly. So we're going to now say that we have we're going to call them L and what we're going to call is we'll call them L and R and also T and B, which are R4 rectangles. These can be either R1 or R2, so they lie within the sets of R1 and R2. And essentially, we know that a collision has occurred if L.x2 is less than R.x1. Oh, wait, hold on, no, it's R.x2 is less than L.x2. No, R.x1 rather. And then B.y1 is less than T.y2. If those two conditions are held true, then we know that the two intersect on the x-axis and the two intersect on the y-axis, therefore the two rectangles must intersect. And that's the mathematical equation we use, I'm using at least, for my most basic rectangle intersects rectangle code. So there we are, and that's how we're doing it in game utils. So you can see that we can now use that to essentially decide whether or not any two rectangles are colliding with each other. And the applications for that are, in most circumstances, just allowing two shapes that are fairly regular in shape to hit each other and see whether or not they coincide. So we can use rectangle intersects rectangle in usually in what we refer to as coarse grain collisions, where we want to see whether or not two shapes roughly intersect, and when that's the case, we can use some more fine grain stuff later on down the track. Question? You can ask your questions by the mic, that's fine. It's just the noise when I'm talking that bugs me.
I'm sorry for the noise. I have a bad mic, but
That's fine.
you know your brackets by the LRTB, right there on your monitor. Are you? I don't understand why you're putting the Are you using it for grouping, or are you using it for the for a table that you're gonna access later?
I'm sorry. This was because there's no. It's a symbol. It means set contains. So it's contained within the set, or they belong to. So again, it's just a simple notation where we say that R1 and R2 are two rectangles that exist as a universe, and in this situation, these four shapes here can be either R1 or R2. Again, this isn't valid Lewis syntax, it's mathematical syntax. And it's very bad mathematical syntax because I haven't got the right characters for it, so I should probably say can be either.
Okay, thanks.
That's probably better, yeah, so sorry for the confusion with that. Yeah, that would be the more appropriate way of saying that, but
Okay.
yeah, cool. Alright, so yeah, that's that as well. I keep saying coarse grain and fine grain a lot, and that might be confusing you guys. The thing is that detection particularly in Ramsden, but certainly in a lot of other ones, is a massive draw on the resources of your system, and having large amounts of it in sort of very complicated levels is extremely sort of resource consuming. The next kind of collision detection we're going to be looking at is going to be pixel-to-pixel collision detection, and what that literally means, it sounds really complicated, so it's what we're going to say it's called, it's what we often call per pixel collision detection. And what that literally means is if we're doing per pixel collision detection at its most basic level, is essentially we're taking any shape that we want to, which might be like a, might have like a little planet here or something. Not a very good planet. Good enough. And then you might have a an asteroid over here or something. Yeah. And per pixel collision detection essentially means that you take the rectangle or the shape that your thing is surrounded by. You then take the shape of the other one that you've got. And then you go step by step. You choose the first pixel here, see whether or not that contains anything, and if it doesn't, then you go up to the next pixel. So we have here, and then what you want to do is then you want to go through every single pixel in the other shape, looking to see whether or not two of those pixels share the same coordinate. Alright, and then when that fails, you go on to the next pixel, and then you see if that pixel has a particular shape that we're going to be looking at, and then you go through every single one of these, see whether or not one of those is contained, then you go to the next pixel. As you can see, that's a really big job to do. In fact, we refer to that as being a kind of equation. Hold on, we're just going to go... If you think about a pixel, essentially, it's typically, if you have like shape 1, we're going to call that shape 1 or just S1, has n pixels, and then shape 2, S2 has m pixels, then that is nm comparisons. And that's using, as I said beforehand, a point intersects point form of collision detection. And if perhaps a more common notation you might have seen beforehand is that if the two shapes have both have the same number of pixels, which is n pixels, then you have n squared comparisons, which is an expensive operation to do in most of the case. If you think about our rectangle collisions, we are comparing essentially, we look in our code here, we're comparing two numbers in this. Well, we've done two comparisons here beforehand, so that's 4 if you want to be sort of technical, so that's 2 there and then 2 there. So that's a total of 4 comparisons. Here, like, if you have 4 pixels in one shape and 1 pixel in one shape, then you've already done as many comparisons as you would for a simple rectangle collision. If you have 30 pixels in one shape, this is probably, if you have like 30 pixels in one shape and maybe 50 pixels in another shape, and that's a very feasible size for a sprite. That might be like, sort of 5 by 6 for one, and then this might be 5 by 10 for another, which is a perfectly reasonable size for a basic sprite, at least in Computercraft, and in real games this is a very, very small sprite. Then that essentially means you have 30 times 50 comparisons. Now, who can do the math on that one? 1500. That's 1500 comparisons. That's like a lot of comparisons. So that's compared to the amount of work that you have to do for just a standard rectangle collision, it's a very, very large amount of work. So if you think about this, if you're doing this for every single sprite in your scene, and you have like maybe 5 or 6 sprites flying around, lots of different enemies, and you're comparing every single one pixel by pixel with that size of a sprite, it means you're now doing a huge number of comparisons, which is why this is very rarely done. Because if you're doing that comparison all the time, your program is going to be slower and slower because it's doing so much work. As a consequence, it's going to hurt performance. So, yes, correct, Wally. Yeah, so 1500, which is exactly right. I'm sorry, Brainstorm, but this is pretty much all math at this point. We're almost divorced from programming at this point. So yeah, so if we have these sorts of comparisons going, we're talking about a huge amount of work. We have to recognize that if we're still doing, thousands of comparisons over and over again, this is eventually going to start to hurt the performance of our application. We can't keep this up in a smooth way. So we have to find a way of being able to sort of limit the amount of work that we're doing. I've done this sort of fairly cleverly in game utils. So actually, if I have it here, I hope I do. Yes, I do. Let's just take a look at the way that I've done it in game utils, because this might be useful to you guys or not as a level of efficiency. When I say coarse grain, fine grain, what that literally means is that if I want to make sure that my collision is a quick one and try to use... Yes, thank you, Curtis has got it exactly right. The thing is, if we have a lot of sprites in the scene that are like 3x5 or 3x3 or however many sprites we have, then what we can do is we can simply say, all right, what if I just take all the rectangles of those shapes and see whether or not any of those collide. And if they do collide, then we can perform pixel collisions on that. And that means we only have to do 1 or 2 of those as opposed to having to do like 20. But there's actually even more we can do to try and make this a more efficient operation, which is what I've done in this code to try and make it as efficient as possible. And this is done for a couple of reasons. So if we just open up, where are we? It's a little bit further down, I think. Next A, previous A. Okay, that's the bounds, so we're getting there. Alright. Creating the rectangle. So this is the code that we have for that R collides with code here, and you can see that this is just what I was talking about beforehand. This is about finding the leftmost and rightmost rectangles quite clearly. Then we just find the distance between those to see whether or not they're colliding, which is all that we've done there, which is totally simple. So what this does here when we want to do a pixel collision is essentially we do the same thing we would do for rectangle collision. That is to say that we perform a rectangle collision first. It is very simple. What we do is, first off, we perform that rectangle collision first, exactly as I showed you beforehand. So we just find out where those topmost edges, the bottommost edges are, and all that sort of stuff. Then what I've done here is I've found the distance, and so that's just done by taking that leftmost and rightmost edges, finding out whether or not those two edges essentially coincide. So if we have a distance greater than that two, so if this doesn't fail, then we know a collision has occurred in the rectangle sense. Then we can do a pixel collision to see how that works. And the way that we do a pixel collision in this case here is we actually create, as you can see here, we measure from the rightmost edge of the X all the way up to the distance of that plus the distance on the X. So what that literally means, if you think about this in terms of a picture, oh damn. What this literally means is if we have a rectangle like this, for example, yeah. And then we have a second rectangle, which is here. The thing is, if we know those two intersect, we don't have to test every single pixel in these two rectangles because we know that the collision only occurs within this space here. So what we can do is we can just take the edges between this edge here, that is to say it's the X, the leftmost edge, and then the leftmost edge plus the difference between these two edges, which is here, and we can do the same thing for the topmost edge. So we take the topmost edge, which is here, and then the topmost edge plus the difference between the topmost edges and the bottommost edges, which is here. And you can take this rectangle, and this rectangle now becomes the area in which we do our pixel collision in. And that's reduced the space from being this massive space all the way around here to this much more manageable space inside of here. And that makes the whole process substantially more efficient and much easier to do. So that way we can actually perform a lot of, 2 pixels down from essentially how many this is. This looks to me like about, I don't know, this looks about sort of 8 or 9 by 5 or 6, probably about the same there. So this could be sort of in the thousands of collisions, that's dropped it down to maybe 2 or 3. So that's substantially more efficient in terms of the way that we're testing. And I mean, the good thing about this sort of approach as well is you can even have it so if you do like a really massive, have a really huge rectangle, like this, for example, and then you've got another really massive rectangle, over here, if they're mostly full, or if you can assume something about the state of those, then it's unlikely that a collision will occur any more than a little bit in without that detection. And even then, that's still a very manageable size of rectangle, even if the collision of those two together would be completely unfeasible. I'm sorry, Wally6, I'm not quite sure I understand you.
Oh no, he was just saying. Oh, I thought you were talking to me.
Oh, do the edges count? Okay, that's entirely up to you. This is just a pictorial representation. It depends on your on the way that you've implemented your code. So, I mean, in the case of like if you if it just depends on how you draw the bounds. If you draw like a this is getting really messy. I'll just go better. If you have like an asteroid that kind of looks like this. There we go. I tend to define bounds, or at least what the bounding rectangle would look like, being this. So I tend to make it the outside, so that way everything contained within the rectangle is considered to be within the space, and everything outside or existing within the rectangle space itself is not. So I'll just clear that up a bit. And there. But like I say, it depends on how you draw your shape. So yeah, it's up to you in that case there. But yep. So that's a nice way, again, like I say, of optimizing your collisions to make sure that you have as little space as possible being used and trying to maximize the amount that you can still test with it as well. So I might just talk very briefly about a few other techniques of collision detection. I won't talk about the implementation so much because they're more complicated, but this is for 3D games rather than for 2D ones. So it's less applicable to computer craft, but it's still important to recognize because well, they're techniques that are going to be used, and you guys should know how to make real games, as well as you should be able to know how to make these games. So we're just going to talk about them very briefly. Just really briefly, so... Alright, so do you guys know much... Oh, well, with whatever you want, really, if you want to learn how to program in 3D. I'm just going to talk very briefly about some of the different techniques that you can use when looking at 3D shapes as opposed to 2D shapes. And it's important because if you look at Minecraft is a 3D game. We live in a 3D world here as well. It's a very standardized 3D world. I mean, it uses these voxel representation, which makes it much easier to do collision detection because, well, voxels are very much like pixels in many ways. We just have just a shape that occupies a particular space, and we can use things like, well, like point intersection to see whether or not two voxels intersect. And it's actually impossible for two voxels to intersect because they are all in sort of they're in very separate sort of structures and things. It's impossible for them to sort of touch one another. So it's a much easier environment to work in. We have 3D things just to see whether or not your 3D shape sort of hits a voxel or not, and that decides whether or not you can pass through it or not. But yeah, we won't go into too much detail about that. We're just going to talk about some of the most basic situations. So if we have any standard 3D shape, let's just take a cube. So take my monitor if you like, a shape like that. You can see that this shape in terms of 3D space is made up of a few different things. It's typically not considered to be simply just like a shape. It's tended to be made up of what we refer to as, I'm going to write these things down, vertices. These can also be called points. And these are essentially the points that define the corners of our shape. So there's a vertex up here, there's a vertex over here, there's a vertex down there, and there's a vertex over there, and then there are 4 in the back. So this shape altogether has 8 vertices. That is 4 for the front face, 4 for the back face, if you like. Then we have lines. Lines connect 2 vertices together, and exactly 2 vertices together. So you can see there's a line that's being drawn from this bottommost face, bottommost vertex to this vertex, then up to this one, then up to this one. So there are, again, you can see there are 4 lines at the front of the shape, then there are 4 lines at the back of the shape, and then of course there are 4 lines connecting the front to the back. So that means there are a total of 12 lines in this particular shape here. So, yep. And then we have faces. And it depends, it depends on what kind of 3D you're working with. Usually, a face can only be made between 3 vertices, and that creates a triangle. So a triangle would be formed, so in a typical case, you might have a triangle being formed from this corner here, up to this one here, then up to this one, so there'd be a sort of a triangle for this face. Then there would be a triangle for the second face, that would make up the 2 of those. Then you would have, essentially, so if you think about it, for every face on our every flat face would be on this, would go to each individual edge there as well. So you have a total, in this instance of having 6 faces, that would be 12 triangles, or you would have 6 if you're working with squares, which depends on what you're working with. Would this not apply to a sphere? Yes, it would. I wish I could draw you guys a picture of how that would look. If you actually, no, what we'll do is, we'll do this online, because we have this. If you just quickly open up a web browser here, yeah, no, definitely do this. Just quickly fire up a web browser and go to Google and search for an isosphere. ISOSPHERE. I'll just write that down for you. And that's a common way of representing a sphere in essentially in 3D represented just with triangles. My web browser is not opening, but I can't find a good picture. I'll have to rely on memory. But what they'll usually do is they will create a series of points that sort of move smoothly around it, and then they'll sort of create triangles in different things there. That's a good one, so yeah. Yeah, you'll find a couple, hopefully, which should be good. But yeah, so that's typically how we represent a sphere with those sorts of shapes. And so when we're colliding, essentially we know that we have, what we're working with typically, in this instance here, is we're looking at essentially vertices, lines, and triangles. There are also planes, which another mathematical concept essentially just means a flat space. So if you think about this, this is kind of a plane in itself. So that could be possibly made up of multiple triangles, and that would be depending on the way that you represent it, and that would be a separate representation in your 3D world. But essentially, you could say that this is one big. Essentially this face of the monitor is one big plane. You have one over here as well, and so on and so forth. It's a fairly basic. You have to look into the maths more detailed. Unfortunately, I won't do that because we haven't got the time today. We'll quickly sort of fire through it. So the way that we can sort of do our basic collision detection, if we want to look at the collisions of things like this, is we can see whether or not if a line intersects a plane, or if a line, like that. So if we can find like a big long line that's being moved in one direction, and if that hits a flat surface like that, then we know it's collided. You'll see this most commonly in shooting games, and this is really funny, because as opposed to having a bullet in a lot of games as being an entity that is measured as it moves along, a lot of games will actually evaluate, whenever like you fire your gun, it will actually evaluate that as creating a line that moves from the tip of your gun all the way out to the distance, and then wants to see whether or not that line intersects with any planes. Like, for example, if an enemy has a shape that's like a flat face like that, it would use that as an example, or if like there's a bit of wall that would have a plane in front of it as well, so the bullet would hit that. And it's really funny, because you'll often see in some cases where that ray will be implemented, but it will still have an animation or a display showing the bullet moving along the screen. And so I've had cases where you'll actually see the person fall down as though they've been shot, even though the bullet has yet to reach them. And you'll see that a lot in these sorts of games, because it's being evaluated using that sort of style, even though the animation is being used a totally different style. So yeah, it's an example of the way in which you can optimize it. If you think about it, evaluating whether or not a line intersects a plane just means you have to just check each individual plane that you're passing by just the once. Whereas if you're evaluating a bullet, it means you have to perform that test every single time your screen updates, which is a lot of times. So in more hectic fights, it means you might have lots and lots of those collisions being tested at once, which is very inefficient. So yeah, that's a way that we can sort of try to make that a bit easier. Very often you create what we call a bounding rectangle or a bounding sphere. And essentially what you'll do, and this is actually the way that Minecraft is going to work. So I mean, if you look at our avatars, they have a complex shape. And we've got like a few different facets and things. You know, we have like a head and we have arms and things. But we're really just being evaluated as a rectangle. As like a large one. I'm not sure how detailed Notch goes into his collision section, but I think you can find that you'll be able to put your hands and things inside of walls, I believe, if you're sort of careful about it. I think you can. Yeah, well, you can go ahead and test now. I think you can. Yeah, okay, yeah, things like that. And you can also, like, I think you can move your avatar in a way that, like, when you touch to one side, you actually find that, yeah, you're partially eclipsed and things. So, yeah, I mean, you can see Wally 6 there, as mentioned, his arm is actually inside the wall there. Because I believe that Minecraft uses your body, just your essentially your central rectangular body as its primary bounding rectangle. And so it's just a matter of detecting whether or not that rectangle intersects any of the voxels in the screen. And if it does, then it's considered to be occlusion. Otherwise, it's not. So, and that leaves that sort of very smooth movement that you can have along the edges there as well. So we have that as a typical instance where not a rectangle intersects another shape, in this case perhaps another rectangle, or rectangle intersects sphere. So if you're using a sphere as a representation, and a sphere is a very easy thing to define because it really just has a center and a radius, and you can then just use a very basic algorithm to see whether or not a point lies within that. So you can just use that for the same thing for rectangles and apply those concepts outwards, which is, let's say, it's a very basic technique. And if you look at some video games, particularly older ones, you'll often see like shapes for like airplanes and things. They look like complex because they're quite nice shapes. And then you'll see the bounding representation, and it's just like thousands of tiny spheres that sort of dot around the edges and things. Again, just to make the occlusion detection a little bit easier to use. So yeah, there's a few different approaches that we can use there in terms of colliding things in 3D spaces. And those can all then be applied using very similar techniques that we actually use for the 2D shapes. Like I say, you can represent a 3D rectangle using similar references. You just have an extra dimension to compare, so some of these instances will work exactly the same way. Yeah, and same thing for line sections with planes and things, and using the same process we did for point intersection as well. So they all hold true, and the techniques that you're learning here can actually still be applied in real large 3D games as well, which is a sort of a cool thing. So yeah. Listen, it is coming on about 10 o'clock, so I'm going to call it a morning for now. So thanks very much for coming. That's somewhat useful. Learned something a little bit interesting. I think what we're going to be doing on Friday is we're going to be applying these techniques of occlusion detection in terms of points, rectangles, and pixels. We're also going to be looking at some specialized forms of occlusion detection, which refer to comparing aspects of the environment with the user and deciding how to sort of whether or not they collide or not. And we're going to be using that to make a platformer, Mario style. So we're going to be doing that on Friday. So hopefully you can come to that, and we'll make one of those. So that'll do for now. So thanks very much for coming, and we'll see you later, I guess.